We're going to look at finding the volume of a solid using disk method. In the first figure, the blue section, this is the area between a function and the x-axis. This beige rectangle is the representative rectangle. In the middle diagram, once it starts rotating, that representative rectangle forms a disk. As you slide that representative disk up and down the figure between A and B, you create a series of disks, and we can approximate the volume of revolution using the sum of all those disks. Now, we're going to look at a little more efficient techniques, but this is to get us started. The disk method to find the volume of a solid of revolution. With the disk method, use one of the formulas below. If you have a horizontal axis of revolution, and that means you're revolving around the x-axis, then your volume is pi times the radius squared, the radius being the function height. The width is delta x. We translate that to dx. Remember that the area of a circle is pi r squared. We add in volume once it starts rotating. That rectangle, this rectangle starts rotating and it becomes one of those disks you saw in the figures above. If we rotate around the y-axis, then we calculate pi times radius squared with respect to y. But we will look at how far up and down, how much of the y-axis gets covered, and that'll be C to D. Let's look at our first example. Find the volume of the solid formed by revolving the region bounded by the graph of f of x equals square root of sine x. To the right, we have the two-dimensional graph where we have a representative rectangle. This graph in black, that's the graph of square root sine of x. Between 0 and pi is where we're investigating. Capital R, that's the height of the rectangle, that's your function. Dx is delta x. And once it starts rotating, the figure below, once this is rotated, we get a three-dimensional shape, and we can find volume. Since capital R is our function, when we calculate volume, we have pi r squared. Your function is r, and we're integrating between 0 and pi. Square root of sine x, quantity squared, is sine x. The antiderivative of sine x is negative cosine x. Using fundamental theorem of calculus, we plug in pi, subtract, plug in 0. So that gives us pi times negative cosine of pi minus negative, that's why there's a plus sign here, cosine of 0. Cosine of pi is negative 1, negative 1 is positive 1, cosine of 0 is 1, so that gives us 2 pi. That gives us the volume of the shape at the bottom right of your screen. Okay, now let's change. We're still going to do the same thing. We're going to calculate volume, but this time we're going to switch up functions. We have function f of x equals 2 minus x squared. That's a parabola. G of x equals 1. That's a horizontal line. And we're going to revolve that about the line y equals 1. So to the right, this arch, that is the graph of 2 minus x squared minus 1. Notice that this rotational axis is also 1. So we have our capital R. Below that is G, but we're not having to worry about that too much because once this rotates, we're going to get the figure. Let me zoom in a little bit. At the bottom right of your screen, once this figure starts rotating, then we get this shape. That beige rectangle becomes this beige disk. We're going to integrate it from -1 to 1. And so the height of this beige rectangle is your function minus the 1. See, we don't go all the way to the x-axis. So it's this height. Basically, what you're doing is you're taking the entire height, which is your function, and you're subtracting back the part you don't want to calculate. 2 minus x squared minus 1, that's 1 minus x squared. Integrating, this will be, let's see, let's square it first. That'll make it easier than integrating first. 1 minus x squared times itself is 1 minus 2x squared plus x to the 4th. Now we can integrate. Let me scroll a little bit. Here we go. All right, so I've got pi times my height of the beige rectangle. It's already been squared out. Integrating, that's x minus 2/3 x cubed plus 1/5 x to the 5th. Using fundamental theorem of calculus, we're going to sub in a 1 minus, and then we'll sub in a -1. Pi times this transaction, plugging 1 in, minus plugging -1 in for all the x's. Once the calculations are all final, we have 8/15 minus -8/15. That's a positive 16/15. Don't forget to multiply by pi. This is the volume of this figure. Let's also look at a technique finding volume of revolution, but it's called the washer method. In the previous two examples, we always rotated around either a fixed line or the x-axis. Sometimes you'll rotate, but it won't be against the horizontal axis of revolution. And what you'll find is sometimes you'll come up with a washer. So if that's the case where the width of your rectangle, that'll always be delta x as long as you're using horizontal axis of rotation. But from the function down to the axis of revolution, that's your capital R. And if there's a gap, that's lowercase r. Once you revolve that rectangle, you get a disk with a hole in the middle. Capital R minus lowercase r. And this is how you figure the volume. The volume will be pi times capital R, the outer radius, minus the inner radius. So you will have a little cutout, and that's why you subtract that little r. So pause if you need to and write this formula down. This is for the washer method. The one before was a disk method, and it's all a matter of whether your function and revolution touches that axis of rotation. This figure at the bottom left, this is a case of where you have two functions and you only have a small representative rectangle, but once it's rotated around the axis, see over here where we're rotating around the axis, there's a gap and there's a hole. So if you think about this, it's like a lampshade turned on its side. There's actually a hole here. So this shape, and you can still calculate the volume because it's a three-dimensional object. Let's look at some examples. Okay, let's look at this example. We're going to find the volume of the solid formed by revolving the region bounded by the graphs of y equals square root of x and y equals x squared about the x-axis. I don't want to zoom in too far. Let me zoom out just a little bit, actually. Here we go. Okay, so to the right, you have the top part of this is the graph of square root of x. The underlying function is x squared. Those are labeled. These two graphs intersect at the origin and at the point 1, 1. Notice that square root of x and trapped below by x squared gives us a representative rectangle, but when we're revolving around the x-axis, that's going to create an open washer. So this figure below, that's what the shape's going to look like once we start rotating it. Capital R is your top function, that's square root of x. Lowercase r is your underneath function, that's x squared. So to the handwritten part, our volume is pi times capital R squared minus lowercase r squared. We're going to integrate from 0 to 1. Those are the values of x at the intersections. Square root of x, quantity squared, is x. X squared is x to the fourth. Integrating, that's half x squared plus 1/5 x to the fifth. Evaluated at 1 minus evaluated at 0, that's going to give us 1/2 minus 1/5 minus, when we sub 0 in, we just get a balance of 0. So that's a half minus a fifth, that's 3/10 times pi, and that's our volume for this solid of revolution. Be sure that you see that once this starts rotating, it doesn't rotate against the x-axis like the disk methods did.